One team of astronomers says it weighs 100 billion times more than our sun. Another team says 20 billion. Same black hole, same data. Answers that disagree by 500%. And if the bigger number is right, this single object is less dense than the air you are breathing right now. This is Phoenix A, the most controversial black hole in modern astronomy. And by the end of this video, you will understand something about it that most videos get completely wrong. In our last video, we went deep on TON 618, the black hole that held the record for decades at 66 billion solar masses. Except that number has been revised. New measurements now place TON 618 closer to 40 billion. Still a monster. But the throne is not as solid as the internet thinks. 5.8 billion light-years from Earth, buried inside the most violent galaxy cluster ever recorded, something might dwarf it entirely. Or it might not. That uncertainty is not a footnote. It is the entire story. Here is what this video covers. The raw scale of Phoenix A, because the numbers will break your intuition. The system that feeds it has no parallel anywhere in the observable universe. How something this massive could exist when physics has rules designed to prevent it, and the fight over its actual mass. Let us start with size. At the lower estimate, 20 billion solar masses, the event horizon would sit about 400 times farther from its center than the Earth sits from the Sun, deeper than the orbit of Pluto, deeper than where Voyager 1 is right now, after nearly 50 years of flight, deeper than where the solar wind finally fades into nothing. And that is the conservative number. At 100 billion solar masses, the event horizon stretches to nearly 2,000 times the Earth-to-Sun distance. The inner edge of the Oort cloud. Light would take 11 days just to travel from the center to the boundary. You could place every planet, every moon, every probe humanity has ever launched inside this single object, and they would vanish like dust in a cathedral. At that scale, traveling at the speed of light along the circumference of the event horizon would take 71 days. Not 71 seconds. 71 days at 300,000 kilometers per second. And a beam of light trapped in orbit at the photon sphere just outside the event horizon would take over 3 months to complete one loop. An orbit measured in seasons, not milliseconds. Think about that for a second. And now, the part that should not make sense. At 100 billion solar masses, the average density inside that event horizon drops to about 1/600th the density of AIR. Not rock, not water, air. The stuff in your lungs right now is 660 times denser than the interior of the most massive black hole ever claimed. The most inescapable prison in physics is, on average, emptier than the room you are sitting in. If that number broke something in your brain, hit like, because it gets stranger. This happens because of a simple rule. Double the mass of a black hole, and its radius doubles, but its volume grows 8 times, so density drops by a factor of 4 every time the mass doubles. At the scale of Phoenix A, the math gives you an object less dense than hydrogen gas, less dense than the faintest wisps of atmosphere 50 kilometers above Earth. And yet absolutely nothing inside that boundary can ever leave. The violence softens, too. A small black hole, 10 times the mass of our sun, would tear your body apart from millions of kilometers away. Astronomers call that spaghettification. But at 100 billion solar masses, the tidal force on a human body at the event horizon would be 50 trillion times lower than what you could possibly feel. To hover just outside this event horizon, resisting the pull, you would need engines producing about 15.5 times Earth's gravity. Nearly double what a fighter pilot endures in combat. That would kill you. But if you simply fell through, freefall is weightless, even at the point of no return. You would cross that boundary and notice absolutely nothing. No wall, no flash, no warning. And once you crossed it, depending on how you fell in, you would have somewhere between 8 and 18 days of personal time before reaching the singularity. 8 days if you fell from deep space, 18 if you started from rest at the edge. Either way, days and weeks of falling through a space that no longer connects to the outside universe. A small black hole gives you 30 millionths of a second, but none of that matters if we do not understand where this thing lives. The black hole is only half the story. The Phoenix Cluster is a swarm of galaxies bound together by gravity, 5.8 billion light-years away. It was first spotted in 2010 by a telescope at the South Pole, scanning for faint distortions in the oldest light in the universe. Immediately, something looked wrong. This cluster is the brightest source of X-rays of any galaxy cluster ever detected, roughly 10 times brighter than the famous Perseus cluster. The gas between its galaxies is superheated to over 100 million degrees. In most galaxy clusters, that hot gas should gradually cool down, collapse inward, and form massive numbers of new stars. But in nearly every cluster we have studied, that does not happen. The central black hole stops it. It swallows some of the falling gas, fires jets of superheated material back out, and reheats the gas before it can collapse. A thermostat, a self-regulating system. Every major galaxy cluster we have observed follows this pattern. The Phoenix Cluster does not. In Phoenix, the thermostat has broken. The jets are firing, but they cannot keep up. The hot gas is cooling and collapsing inward at a rate that has no match anywhere else in the known universe. The central galaxy is forming 740 new suns worth of material every year, averaged over the last 100 million years. That alone is extraordinary. Most galaxies at the centers of clusters form fewer than 10. But the James Webb Space Telescope measured a more recent snapshot, and over the last 10 million years, the rate has climbed to over 1,300 solar masses per year. It is not just extreme, it is accelerating. Now here is the number that explains all of it, and that no other video about Phoenix A has ever mentioned. Astrophysicists use a simple ratio to test whether the hot gas in a galaxy cluster is stable. It compares how quickly the gas can cool to how quickly gravity can pull it inward. In every system ever measured across hundreds of galaxy clusters, that ratio stays between 10 and 20. The safety valve holds. No known system had ever pushed that ratio below 5. Phoenix pushed it to 1. The gas is cooling exactly as fast as it can fall. There is nothing left to hold it up. The hot atmosphere around the central galaxy cannot resist gravity anymore. It is raining inward, condensing into cold filaments, feeding both the starburst and the black hole in a runaway collapse that the jets cannot stop. Phoenix is the only known place in the observable universe where this has happened. And we are watching it during a window that lasts roughly 100 million years. That sounds long. It is less than 1% of the age of the universe. A brief flash. We caught it by accident. And in February of 2025, the James Webb Space Telescope gave all of us the clearest picture yet. A team led by Michael Reif pointed the James Webb Space Telescope at the core of the Phoenix Cluster for 12 hours and mapped a specific wavelength of light from neon gas at about 300,000 degrees, the critical temperature between the scorching X-ray plasma and the cold gas that forms stars. No telescope had ever imaged this middle step in any galaxy cluster before. The cooling rate through that intermediate zone came back at 5,000 to 23,000 solar masses per year. Far more extreme than even the X-ray data had suggested. For the first time, we could see the entire feeding highway, and the flow is even more violent than anyone predicted. If this is the kind of science content you have been looking for, no clickbait, no hype, just the real data, subscribe. This is video 3 in our Cosmic Extremes series, and it goes deeper from here. So how does a black hole get this massive? Physics has two rules that should prevent it. The first is a speed limit on feeding. When a black hole pulls in gas, that gas heats up as it falls and starts radiating energy outward. At a certain rate, the outward push of that radiation equals the inward pull of gravity, and the gas gets blown away. The black hole chokes on its own meal. There is a maximum feeding speed, and it caps how fast any black hole can grow. The second limit is about size. In 2016, the physicist Andrew King calculated that as a black hole grows, eventually the disk of gas around it becomes heavy enough to collapse under its own weight, fragmenting into stars instead of feeding the black hole. King found this happens at around 50 billion solar masses. Beyond that point, the gas tears itself into stars before it can be swallowed. The black hole goes dark. If Phoenix A is 20 billion solar masses, it sits below that ceiling. If it is 100 billion, it has blown past the limit by a factor of 2. And that demands an answer. The leading idea is something researchers call cosmic rain. In most systems, gas flows toward a black hole in a smooth, orderly disk. But when the hot gas in a cluster cools fast enough, it becomes unstable. Instead of flowing smoothly, it condenses into clumps, cold clouds, and long streamers that fall inward from random directions. These clumps collide, cancel each other out, and plunge toward the black hole in chaotic bursts. This can boost the feeding rate by a factor of 100. Because the flow is full of gaps, radiation can escape between the clumps while the dense clouds punch through the radiation barrier. Phoenix, where the gas is cooling as fast as gravity allows, is the single best candidate for this process anywhere in the cosmos. But here is where the story turns. Everything we have discussed depends on a number that astronomers cannot agree on. How much does Phoenix A actually weigh? In 2012, Michael McDonald and his team estimated the mass using established scaling relations, statistical patterns that link how fast a galaxy's stars move with the mass of its central black hole. The relationship is well established in closer galaxies where we can measure both. Applied to Phoenix A, it gives roughly 20 billion solar masses. That result is consistent with similar systems, but it is not a direct measurement. In 2016, Michael Brockamp used a completely different approach. He treated the galaxy as a fossil record. When a growing black hole flings stars out of its core, the empty zone left behind acts like a footprint. Brockamp combined that footprint with the extreme jet power and calculated that, under assumptions of low radiative efficiency, the black hole could reach 100 billion solar masses. That is the number that made headlines. And this is the number that carries the biggest question marks. If the efficiency is typical, the mass drops sharply. If the black hole spins fast, it drops further. It is an upper bound built on a chain of assumptions, not a measurement. And there is a cautionary tale. In 2019, the black hole in a nearby galaxy called Holm 15A was measured using the gold standard, directly tracking the orbits of stars around it. The result was 40 billion solar masses, the verified heavyweight champion. Then, in 2025, a new team remeasured it with better instruments and a more realistic three-dimensional model of the galaxy's shape. The new number came back at 22 billion, roughly half. Even the most reliable technique we have was off by a factor of 2 when the modeling improved. If that happens at 700 million light-years, think about what it means at 5.8 billion. Phoenix. A is 30 times farther. No existing telescope can resolve its core. Even the Event Horizon Telescope, which imaged the shadow of the black hole in M87, cannot help. Phoenix A's shadow would be thousands of times too small to see. So where does it rank? The most robustly measured heavyweight is now Holm 15A at 22 billion, measured by watching stars orbit. TON 618 sits at roughly 40 billion. A new contender called the Cosmic Horseshoe, discovered in 2025, comes in at 36 billion. And Phoenix A sits somewhere between 20 and 100 billion, a range so wide it contains the entire competitive field inside it. Some astronomers argue the lower number is closer to reality. Others believe the extreme environment we just walked through justifies an extreme mass. After watching this video and our TON 618 deep dive, which do you think is actually more massive? The one we measured directly or the one we inferred from its footprint? Drop your answer in the comments, because this is the debate playing out in astrophysics right now. Here is what we know for certain. Phoenix A lives inside the most extreme environment of its kind ever discovered. It sits in the only known system where the hot gas atmosphere has reached its absolute cooling limit, a record that is not contested, not estimated, but directly observed. Stars are forming around it at a rate that dwarfs every other system by an order of magnitude. JWST confirmed in 2025 that the cooling flow feeding this region is even more violent than X-ray telescopes had predicted. And the feedback mechanism that should have shut all of this down has not caught up, not yet. Whether the black hole is 20 billion or 100 billion solar masses, it is extraordinary. At 20 billion, it ranks among the most massive ever identified, sitting in a system actively trying to make it larger. At 100 billion, it has broken every theoretical growth model, occupying a volume thinner than air, in a category of object that may not exist anywhere else. And we are seeing it as it was 5.8 billion years ago. The light reaching our telescopes left the Phoenix cluster when the universe was barely half its current age. The sun had not formed yet. The Earth did not exist. Whatever this black hole is now, it has had nearly 6 billion additional years of feeding from the most extreme cooling flow ever measured. 6 billion years of cosmic rain pouring inward. We cannot know what it has become, not yet. What we can say is this: we found something at the boundary of what physics allows. A system where every natural safety valve has broken. A black hole that may or may not exceed the theoretical maximum. And the disagreement over its mass, the factor of 5 gap between two legitimate methods, reveals something deeper than any single number. It reveals how much of what we think we know about the largest objects in the universe is still built on inference. On brilliant, careful, limited inference applied to something too far away, too ancient, and too strange for our instruments to pin down. The universe does not owe all of us a clean answer. Phoenix A is the proof. If this series is changing how you think about the cosmos, subscribe. Next, we leave individual objects behind entirely and travel the full timeline of the future, from 1,000 years to 1 quadrillion, the slow, patient story of how everything ends. That video will stay with you.